Okay, so last section we're going to take a look at, again, is 4.2. We'll do half of it today, and then we'll do the other half tomorrow. So we're going to focus on graphing. So it doesn't mean we're not going to do a little bit of algebra. We might still have to do some, especially when we're trying to find like roots or vertical asymptotes or horizontal asymptotes. All of that's going to be important when we're making a sketch. Okay, so we'll do a little bit of algebra to get the information we need, and then we'll plot that information on a graph. So remember that in a rational function, if you have a common factor in the numerator and the denominator, and you graph it, you could end up with a discontinuity that you can't really notice. What if we called that type of discontinuity in here? Can't really see it on the graph, but it is there. Yeah?
Would it be a hole?
It's a hole. Okay, so if you graph something like x squared plus 2x plus 1 divided by, let's say, x plus 1. You may say, oh yeah, okay, I can see what would make the denominator 0. It's negative 1. And he said yesterday that if the denominator is 0, there's a vertical asymptote. Well, not in that problem. Because if you factor the numerator, it factors as x plus 1, x plus 1. So now you have a common factor in the top and in the bottom. So let me graph it, just so you can see. So x squared plus 2x plus 1, and we're going to divide by x plus 1. And watch what happens when I get close to negative 1. Doesn't look like anything happened. Looks like I just drew a line right through negative 1. But if you go to your table and you type in negative 1, it says error. So there's a hole in the graph. If you check negative 0.99999, you get very close to it, you're fine. You get 1 times 10 to the negative 4th. That's just a very small number. Okay. If you do negative 1.001, again, you get another very, very small negative number. That's fine. It's just at negative 1, there's a hole. And it's an infinitely small hole. So if it's infinitely small, does it exist? It does. Okay, so there is a hole in the graph. So we would normally, if we were sketching it, do this. That's how you show a hole in the graph. I'm not going to graph this one. Okay, I just graphed one to show you a hole. But would this have a hole, or would it have a vertical asymptote at 1? Yep. It would have a hole because you have a common factor. Okay. That would have a hole at 1. How about this one? Hole at 1 or vertical asymptote? Chris?
There'd be a hole at 1.
That's a hole again because you have a common factor in the numerator and the denominator. Now, what if I did that? Hole at 1? Or vertical asymptote at 1. Oh, Casey, what would I have this time? Sorry, did you say anything? I didn't hear you. You did. What would you have? Okay, yeah. Would you have a vertical asymptote or a hole in the graph? You'd have a vertical asymptote this time because the numerator and the denominator don't have a common factor. Okay? So is there any question about when you get a vertical asymptote versus when you get a hole? Okay. So the proper name for a hole in a graph is called a removable discontinuity. Basically, you can think of removable as repairable. If I had a graph like this, and I asked you, is that a continuous function? The answer is no. I had to lift my pencil to draw that. Even if it was an infinitely small amount of time I had to lift it, I still had to lift my pencil a little bit to draw that. That's called removable because all you would have to do to repair that is basically patch the hole. If you filled in the hole, now it's continuous. You never have to lift your pencil. Compare that with a vertical asymptote. A vertical asymptote is not removable. That's not just a small thing you can fix. That's a discontinuous graph. And to try to make it continuous, you would have to connect this to that. That is up at infinity. That's at negative infinity. You can't connect infinity to negative infinity. There's no way to just patch something real small and make it continuous. Okay. So that is not a removable discontinuity. That's a big discontinuity. It's as big as you can get. They're going in opposite directions forever. So any questions why a hole is considered a removable discontinuity? It's a discontinuity that you could easily patch. Just one little thing, and you can fix it. All right, so we're going to be looking at problems like this. Okay, this is, don't write it yet, but that's a sample of what we're going to do. You're going to have a polynomial in the top and a polynomial in the bottom. And that's what I'm representing by this. Okay, this is just the generic way to write a polynomial. Usually you start with the highest exponent, and then the next term, the exponent goes down 1, and then it would go down 1 again, down again, until you finally end up with just a constant with no variable attached. Okay? And the same thing in the bottom. So we talked in chapter 3 about the EBM. Anybody remember what did EBM stand for? Remember that? EBM. We used it to describe what a polynomial looked like. Sometimes it was up, or up, down, up, down, things like that. Remember, Sarah? The end behavior model. And if you had something like this, what would be the end behavior model in that polynomial? Remember, the model itself is a term. It's not like up, down. That's describing the model. I want something I could actually put into Y1 on my calculator, and it would look like that. Yep. 4. Well, the degree is 4. That's the highest exponent. But what's the entire EBM? Yep.
3x to the 4th.
3x to the 4th. The EBM is the term with the highest exponent. So the EBM here is 3x to the 4th. Well, when we want to find an EBM for a rational function, it's basically the same thing we did in chapter 3. Find the EBM of the polynomial in the top, find the EBM of the polynomial in the bottom, and then divide the two. And that's how you find the EBM of a rational function. So in our case, the EBM, the way we usually write it is the first term. That is the term with the highest exponent in the top. Every exponent is lower than that. This is the term with the highest exponent in the bottom. Every other term has a lower exponent than that one. So a sub n x to the n would be your EBM in the top. B sub m x to the m is your EBM in the bottom. And again, b sub m would be a number, like 5, and m would be an exponent, like 3. So 5x cubed. So, the EBM for f of x is, okay, that's what I called this formula, f of x. The EBM is taking the highest degree term in the top and dividing by the highest degree term in the bottom. That's the EBM. So when you divide it, you're going to have a number and a number. So you're going to divide those. A sub n over b sub m. Yeah, those will just be two numbers. And then here you're dividing variables with the same base. Anybody remember the rule when you divide variables with the same base? What do you do with the exponents? Remember? How about Jack? Do you remember what you do when you divide variables with the same base? Like x cubed divided by x.
Would just be x squared.
Right. And so how did you get x squared?
3 minus 1 is 2.
Yeah. So the rule is if you're dividing and you have the same base, you subtract the exponent. Actually, I have it written right there. So a sub n over b sub m, that's the coefficients you're going to divide. And the variable is going to be x, and the exponent is n minus m. So like in this case, x to the 3 minus 1, which is x squared. Now, what would happen if I had something like this? X cubed divided by x to the 5th. What would be my answer there? Well, Matt?
Wouldn't it should be x negative squared?
X to the negative 2, yeah.
Yeah.
Now, the only thing I don't like about that, we followed the rule, which we did it correctly. I don't really want to leave negative exponents, okay, because that's going to get confusing. So what does x to the negative 2 mean? In Algebra 1, you learn how to write that as a positive exponent. So what does it mean when you have a negative exponent? Well, let's look at that a little different. Francesca, what does x cubed mean? Yeah, I don't understand what that means though.
X times x times x.
Oh, so x times x times x. And Casey, what about x to the 5th? Yeah, we multiply x times x 5 times. Now, whenever you have the same factor in the top and in the bottom, you can cancel it out. So Ethan, what can I cancel out there?
3x.
Okay, so I can cancel 1. You said how many?
3.
I can cancel another one from the top and the bottom, and I can cancel a third one from the top and the bottom. What's left in the top? You can't just leave an empty fraction there. You're going to have to leave something up there.
1.
1, yes. So 1 is left in the top. And what's in the bottom?
2.
Chris? What is it?
2
What happened to the x's though?
or 2 x's.
Like this? That's 2x's. 2x.
X squared.
X squared, yes. So look at what we had. And look at what we have here. So what does x to the negative 2 really mean? When you have a negative exponent, where does it end up? Tyler?
It's just the same as x squared.
Well, x to the third over x to the fifth isn't the same as x squared. It's the same as when you divide x to the third by x to the fifth. You don't get this. What did we get?
Oh, so when you have a negative exponent, you just have to divide it by 1. Right? That's it.
Yeah, you put it in the bottom of a fraction.
Yeah.
So when you have a negative exponent, all it means is that whatever is left should be in the bottom, not the top. So this is x to the negative 2. That means you should have x to the positive 2 in the bottom. If you had x, if you had something like 5 to the negative 2, that means 1 over 25. It means you have 2 copies of 5, but the negative means they're in the bottom of a fraction, not in the top. Any question on that? All right, so let's try finding the EBM for f of x. And once you find the EBM, that's how you do the horizontal asymptote of a rational function. Because think about what EBM stands for. End behavior. The asymptote means tell me what's happening to the behavior of the function at the end of it. So that's exactly what the EBM does. All right. So EBM. Zach, what's my EBM of the top?
Top.
Yep.
This would be
What is it?
negative 1.
That's the lowest degree term on the top. We want the highest. Ethan?
2x squared.
2x squared. Okay, that's what we did last week, right? Finding the EBM of a polynomial. So that's the EBM of the top. And Chris, what about the EBM of the bottom?
3x to the third.
3x to the third. Now, if we simplify that, what am I going to be left with? Well, Sarah, can you tell me what I'd be left with?
2 over 3x.
Yeah. You have 2 over, and technically that's x to the negative 1, right? 2 minus 3 is negative 1. That means you should have 1 copy of x in the bottom. Okay, so this is called the EBM of the rational function. Now, let x approach infinity in your EBM, and that tells you the horizontal asymptote. How does the equation of a horizontal asymptote always start? Doesn't matter what the number is going to be after this, but it always starts a certain way, yeah?
Y equals.
Y equals. Excuse me. Okay, so what happens to the EBM as x approaches infinity? What does the EBM approach? And you can think about it as x approaches infinity or negative infinity. The EBM approaches the same thing. Taylor?
0.
It approaches 0. Can you explain why? Why is it approaching 0? So that's thinking about like a vertical asymptote. So we want to, what did I say to let x approach when we're looking at the horizontal asymptote? Actually, letting x approach what? Infinity, right? Just look at what it says, e. E means end. Where is the end of a function? Infinity is the end. It's very far away. So you're letting x approach infinity. So why is the EBM getting closer to 0 as x approaches infinity? What's the EBM here? I want to make sure we know what that is. Someone tell me again, what's the EBM? Yep?
2 over 3x.
2 over 3x. And to find the horizontal asymptote, we're letting x approach what number?
Infinity.
Infinity. So as x approaches infinity, what happens to the denominator in that fraction? Yeah.
It keeps going up.
Yeah, it gets really big, right? If x is 1,000,000, then the denominator is 3,000,000. If x is 1,000,000,000, then the denominator is 3,000,000,000. So the denominator is getting really big, which causes the fraction to get what? Yeah,
Smaller.
really small. So as x approaches infinity, the denominator is getting big, and you're taking 2 and dividing by a really big number. It will approach 0. Will it ever reach 0? No. Even if you take 2 and divide by 1,000,000,000,000, is that 0? No, it's really small, but it's never going to reach 0. So the first step to finding your horizontal asymptote is find the EBM. That'll give you a simplified formula to look at, and then let x approach infinity in that formula. Let's try this one. Francesca, what's the EBM of the top? So when you pick an EBM, your only choice is to pick an entire term. You can't pick pieces of things. You've got to take the whole term with it. So what's the whole term? 2x to the 4th. If you were to graph this in y1, and then you were to graph this in y2, they would look exactly the same if you zoom out far enough. Okay, that would look almost identical. Right, so the 2x to the 4th is predicting what the top function is going to look like. It doesn't predict all the little details, but if you zoom out to like -1,000 to 1,000 and -1,000 to 1,000 and graph both of these, they're going to look the same. So the EBM is 2x to the 4th. How about Matt? What's the EBM in the bottom?
3x to the 4th.
3x to the 4th. So Ethan, when I reduce that, what is my EBM?
2 over 3.
2 over 3. The x is gone. And that happened because the degree in the top and the bottom were the same. So they canceled out completely. So now, my horizontal asymptote. Y equals. Now, look at what I just clicked on. Look at that fraction and tell me what happens to that fraction as you let x approach infinity? Yeah,
Nothing.
nothing. So what does it stay as?
2/3.
2/3. There is no x. Canceled out. So as you let x approach infinity, it has no effect at all on this EBM. The EBM is a constant. The horizontal asymptote today is always going to be one of two things. It's either going to be 0 if the degree in the bottom is larger, or it's going to be a number if the degrees are the same. Those are the only two things that will happen today. So we are going to specifically look at sketching when the degree of the numerator is smaller, that was the first one we did, or equal, that was the second one we did, to the denominator. When the numerator is bigger, that's a little different. We're going to look at that tomorrow. That's part 2. So here are some general guidelines that will help you with graphing. And you won't really need a graphing calculator yourself to learn this part. You can watch me do it. You will need it in the homework, but just watch me right now. Okay, so one thing you want to try to find, if you can, are the intercepts. Not every graph crosses the x and the y-axis. Here's a graph with no intercepts at all. It gets close to each axis, but it never actually crosses them. So you may not always have intercepts, but if you can find them, you should try to. To find the x-intercept, you let y equal 0. To find the y-intercept, you let x equal 0. That's just how it works. Next thing we want to try to find are vertical asymptotes. Remember, as long as you don't have any common factors, the vertical asymptotes are the zeros of the denominator. Most of the time, the worst case would be you'd have to use quadratic formula. But I would say a lot of the time, you're going to be able to factor it. So there's your verticals. The next thing you want to find is your horizontal. And to get the horizontal asymptote, you need the EBM. And you let x approach infinity. Now, if you find a number that is a vertical asymptote, can you plug that number into your formula? If you have a number that's a vertical asymptote, are you allowed to plug that in? Okay. Yeah?
No, because it makes the denominator 0.
Exactly. Make the denominator 0. So you can't plug in a number that would make it 0, but you can plug in a number close to that. So if you had a vertical asymptote of like 2, what you want to do on the calculator is don't plug in 2, plug in like 1.999 and see what happens. Plug in 2.0001. Plug in a couple numbers around the vertical asymptote that are very close to it. And remember, what always happens near a vertical asymptote is it either goes up to infinity or it goes down to negative infinity. Okay? Always one of those two. Okay? And those are kind of the 4 general things that you can do to make a sketch. So we'll end with trying to do a few sketches. Okay, these sketches takes a little practice. You're probably going to have to plot maybe 5 or 6 points to get a good picture. Maybe more. It depends. All right, so let's see if we can sketch this. So x minus 1 divided by x squared minus x minus 6. So it's degree 1 in the top divided by degree 2 in the bottom. Okay, so let's go right in order. Intercepts. Let's start with the x-intercept. How do you find the x-intercept? What did I just say in the notes? That's when, Francesca?
Y equals 0.
That's when y equals 0. Now, I don't have a y up here, but I kind of do have a y. I'm naming it something else. Can anybody tell me, where is the y up here? Yep, it's the f of x, right? This is the y. So what we're saying is to find the x-intercept, set this fraction equal to 0. Like this. And solve. There's only one way a fraction can ever come out to 0. What has to happen for a fraction to come out to 0? Yeah.
The top has to be 0.
The top has to be 0. It doesn't matter about the bottom. Unless the number that makes the top 0 would also make the bottom 0, then that's a problem. But all you're worried about is the number that would make the top 0. What would make the top 0? Yeah.
1.
1. That's your x-intercept. And if you plug 1 into the bottom, I can quickly tell you're not going to divide by 0, so that's fine. So on our graph, we're going to mark the x-intercept. How do you find the y-intercept? Francesca?
X equals to 0.
Plug in 0 for x. Yeah. Okay. What do you get if you plug 0 in for x in the top? Yeah.
-1.
-1. What do you get if you plug 0 in for x in the bottom? Yeah, Tyler? You get -6. And that gives me a y-intercept of positive 1/6, just above the origin. Okay, so right about there maybe. Okay, so that's not enough to make a sketch, but we got the intercepts. Let's find the vertical asymptotes. Vertical asymptotes are where the denominator is equal to 0. What could we do to the denominator to make it easier to see the roots? Yep.
Factor it.
Let's factor it. So x squared minus x minus 6. Okay, how about Zach? What are my signs going to be here?
Positive, negative.
Yep, we're going to need a positive and a negative. And two numbers that multiply to give me 6. Yeah.
2 and 3.
2 and 3. Let's try them in that order. X squared minus 3x plus 2x minus 3 plus 2 is minus 1. Perfect. So, what are my two vertical asymptotes? Yeah.
-2 and positive 3.
-2 and positive 3. Okay, so let me sketch that. That's how you sketch an asymptote. -2 and positive 3. All right, what else did they want us to find? The horizontal. All right. So to find the horizontal, you're going to do the EBM first. Ashley, what's the highest degree term in the top?
X.
X. And Bailey, the highest degree term in the bottom?
X squared.
X squared. And Sarah, if you reduce that, what do you get?
1 over X.
1 over X. Now, let X approach infinity, and tell me what happens to that fraction. What will that fraction approach? Yeah,
0.
it will approach 0. Okay, so we have a horizontal asymptote at 0. Just because the axis is already black, I'm going to do it in red. Okay. So we've got the x, the y, the verticals, the horizontals. Now we're going to use the graphing calculator to check what's happening near the asymptotes. Okay. Let's type in. Now I need to type this in, and this is where I'm going to use my table. All right, so x minus 1 divided by x squared minus x minus 6. Okay, we know that the vertical asymptotes were -2 and 3. Don't plug in -2 and don't plug in 3. It's not going to work. You get an error. But let's plug in a number that's to the left of -2, just barely. What's an x value that's a little bit smaller than -2, but extremely close to it? Yep.
-2.001.
Yep, that's perfect. -2.001. That's not -2. You can plug that in. And when you do, you're at -600. So that's dropping down to -infinity. Okay. So way down here. All right. Now let's check the other side of -2. What's a number that's just a little bigger than -2, but very, very, very close, just as close as that? Yep.
1.999.
Can you say it again?
Negative 1.99.
Yep. -1.9999. And when you hit enter, you're up at 600. So on that side of the asymptote, the graph is going to spike up to infinity. So all of a sudden, it's going to get very high. Let's check the same thing for the other asymptote. Okay, we're at 3. Can someone give me a number just a little smaller than 3? Yeah.
2.99.
Sure, 2.99. Oh, I hit it a few times. That's fine. 2.99, we're at -4,000. That's dropping down to -infinity. And that's just before the asymptote. Now let's check just after it. So that would be like 3.001. And you're up at 400. So you're going up to infinity. Okay. Now, my graph goes from -10 to 10. So if you wanted, you could do a couple other points. Like -10 is -0.1 just underneath the axis. +10 is +0.1 just above the axis. All right, so let me zoom out so I can see what's happening. This graph is going to be broken into 3 pieces. Let's start with this one in the lower left. You have to stay very close to that dotted line and very close to that dotted line. But those have to meet. So the only way they can meet in this kind of function is if they curve, right, to connect to each other. So it's going to start to go away from the asymptote. It's going to curve down. And then it's going to meet up with the other one, and it's going to keep going. That's what the lower left is going to look like. Now, the upper right is going to do the same thing. It's going to stay very close to the asymptote, start moving away from it. It's going to curve, and it's going to start getting closer and closer to that other asymptote. And now the section in the middle. I have 4 points I need to connect. And I need to stay close to the vertical asymptotes as long as I can. So we're going to stay very close. But we're going to have to start moving away because we're going to connect to these other 2. But then there's a 3rd point down here that I have to make sure I go through. And that's basically what your graph looks like with these kinds of formulas. Might be a little flatter in here than I drew it, but I think if you hit graph, we did pretty good. Okay, so there's your graph. So again, it takes a little bit of practice on those, but you'll see they all look pretty similar. Okay, we'll do one more that it's going to look kind of the same, but then that'll be the last one we do. Okay, questions on that? All right, let's finish up with this one. Okay, this time they've already written out everything they want us to find. Okay, so we'll sketch a graph. Let's start with vertical asymptotes. Does anybody see what I can do to the bottom to make that easier to see my asymptotes? Well, what did we do in the last one about math? Yeah, what did we do to the denominator in the last problem?
We factored it.
Yeah, we factored it. Let's do the same thing here. Let's factor it, but this is even easier kind of factoring. It's not a two sets of parentheses thing. All you can do is factor out a GCF. What's the GCF of the denominator? Ashley? X. So let's pull the X out. And what would you be left with if you factor out an X? Yeah.
2x. Minus 5.
Minus 5. Now set that equal to 0 and solve it. Casey, what would you plug in for X to make the first factor 0? Zero, yes. If you plug 0 in for X, that will make the first factor 0. And what would you get if you set what's in the parentheses here equal to 0? Yep. X would equal 5 over 2. Plus 5 divided by 2. For graphing purposes, it's probably easier to just say 2.5. Okay, so there's my vertical asymptotes. I'll sketch them later. My horizontal. Let's do the EBM. Ethan, what's the EBM of the numerator?
3x squared.
And the denominator?
2x squared.
Good. And Chris, what does that simplify to?
3 over 2.
3 over 2. So there's my EBM. Now, Francesca, how does the equation of a horizontal asymptote always start? Starts with a letter. Starts with a letter. Y equals, good. Y equals. And what's my horizontal asymptote going to be in this one? Look at my EBM and let x approach infinity. What happens to my EBM? Yep. It's 3 over 2. Which is 1.5. Okay, so we've got that. X intercept is when y equals 0. So let's set the new, remember, it just means to do that. The only way that you could set this fraction equal to 0 and solve it is if the numerator was 0. So let's see if we can factor the numerator. 3x squared plus x minus 4. And yeah, that does factor. A lot of times I'm going to make these problems so they do factor. So 3x and x. How about, Tyler, what are my signs going to be?
Plus and minus, minus and plus probably.
A minus and a plus, we can try it. Why don't we try a plus and a minus?
Yeah.
I just have a few. And two numbers that multiply to give me 4 are what? Two numbers that multiply to give me 4. Yep.
2, 2.
Yep. What else?
4, 1.
Yes, let's do 4. So I would try, in that order, let's see what happens. 3x squared minus 3x plus 4x. Perfect. Minus 3 plus 4. So when we solve this, x equals 1 is my intercept, and negative 4/3. So I cross the x-axis twice. 2 X intercepts. Y-intercept. That's when you fill in 0 for x. What do I get if I fill in 0 in the top? Yep,
Negative 4.
I get negative 4. What do I get if I fill in 0 in the bottom? Yeah,
0.
0. So I get negative 4 divided by 0. What does that mean my y-intercept is going to be? Yeah?
0.
No, the 0 would have to be in the top for that to be 0. Yeah?
And then be undefined.
There isn't one. Yeah. This graph will never cross the y-axis. All right. Now I think we're ready to use the calculator and make our final graph. Let's put in our vertical asymptote at 0 and 2.5. There's 0. There's 2.5. And the horizontal was 3/2, which is 1.5. So notice we created that grid pattern, just like you had before. It's going to look almost identical. All right, we've got an X intercept at 1. We've got another one at negative 4/3. The only thing left to do is pick some points near the asymptotes and see what happens. We know we're going to get really big or really big positive or really big negative numbers. Okay, let's see what we got. So 3x squared plus x minus 4. And we're going to divide by 2x squared minus 5x. Okay, we need a number very close to 0, but let's go a little smaller. Number very close to 0, but just a little smaller. Jake?
.001.
Negative 0.001. And we are at negative 8,000. So when you're a little bit to the left of 0, the graph goes way down. When you're a little bit to the right of 0, it goes way up, positive 8,000. This one was 2.5. What's a number that's just a little bit smaller than 2.5? But really close to that. Ethan?
You said smaller?
Yeah.
2.49999.
Yeah, that's really close. You're at negative 35,000. Okay, so you're way down. Like that. And a number just a little bigger than 2.5. Let's do 2.5001. And we are at 34,500. Very, very high up. Okay, so what's going to happen? It's going to go through this point. It's going to start to curve and go that way. Same kind of thing happens in the lower left. It's going to go here. We have an X intercept we want to go through. And then down. And the last one, I'm just going to make it smaller so I can see it. It's going to come down, almost vertical, go through the intercept, and keep going down. Now, I think the calculator is going to have a problem sketching that because it's almost straight up. Remember, when a graph starts to get vertical, the calculator gives up. So let's hit graph and see what it does. I think it's going to give up in the lower left part as well. It's too steep. Yeah. So a calculator couldn't really sketch it the way it should be. That is not what it should look like. It should look like what we did. Okay. And that's rational functions. All right. So those are the problems to take a look at for tonight. We'll finish 4.2 tomorrow after we go over the homework from part 1. Reminder too that I will be after school tomorrow if anybody needs to stop by for extra help.